of mass. This uh, section talks about how if you observe a mass, I'm just gonna draw a square like this, it uh, shape might change, but a mass will remain the same. For example, you can go through a different shaped tube or cavity, but its mass will not change based on the cavity. And we can describe this by saying that the um, mass, which is going to be simply this, oops, as I said, this was the Lagrangian derivative or Lagrangian approach. It will be equal to zero. The change in mass will be equal to zero. Now, of course, thanks to Reynolds transport theorem, we can bring inside our d over dt inside the integral, and then we have our derivative of our rho, or our density over time, plus the derivative of our function rho times the velocity, the k direction, derived in terms of the k direction over a volume to be equals to 0. Alright, what does this mean? Well, since the integral will only be 0 if the inside is 0, we can just say that this part here has to be 0. Well, if you're talking about, for example, about water or something similar, the density over time will not change. But of course, we're talking about fluids, and we're talking about also water. Now, we're talking about also air, so that is compressible. One important thing that we need to think about this is that this says that not only the mass concerned, but then the velocity is continuous, and that's why sometimes it's called the continuity equation, because in fact it mentions that the velocity is continuous. Now, this formula works for single phases of fluids. So we're not talking about any or any like nuclear reaction happening, electromagnetic reaction forces going on the liquid, and there is no change of phase taking place, so that our density does not change. Even though the mass will remain the same, the density would change, but the total continuity equation will still be equal to 0. Okay, so what can we do with this? Well, we can see the first term will remain the same, and the second part we can apply a chain rule. So we're gonna have uk times the derivative of the density over a distance, and then rho times the derivative of our velocity over a distance. Actually, the bottom will be xk, because we're talking about a direction, sorry. And of course, this still equals to 0. But now, what we can see now is that these first terms are just equals to the material derivative of rho in terms of material derivative. And then the second part is just going to stay the same. So now we have k over xk. This is a mixed form of the continuity equation. Now, it doesn't actually help us much to understand this, because it's in two different frame of references. We have a Lagrangian derivative and Eulerian derivative, because the left part is talking about Lagrangian and the right part is an Eulerian derivative, so it doesn't help too much, but it's useful to then plug in this equation in the other ones. However, what we derive that is very useful is this equation right here, the continuity equation, which will pop out continuously in our problems.